In this unit, you will learn the different techniques that can be done to transform a complex term to a term that is more simple to integrate. They are called techniques. Why? Because they are suggested approaches that can be applied in integrating functions that involve specifically special terms. In here, you still have to review your differentiation formulas for products of functions, as the integration formulas, they had been derived from here. So again, pay attention to the algebraic signs of the derivative so that you will not be confused on the coming problems that we will be meeting in this unit. Prior to our discussion of various techniques of integration, it would be nice if you will be remembering, or maybe memorizing would be better, these standard indefinite integration formulas that you learned in our previous modules. This will be occurring frequently in the problems that we will be discussing in this unit. One of the most widely used techniques of integration is this integration by parts. This is actually obtained from the derivative of the product of two functions. If we will try to recall our differential equations, it actually came from the differential of a product. What does this mean? It means that if we take the differential of uv, that is equivalent to udv plus v du. In other words, it is equivalent to the first function, multiply it by the differential of the second function, plus the second function, multiply it by the differential of the first function. Now, what about if we will integrate this equation? If we integrate this equation, we could just simply apply on the left side the properties of integrals, thereby making this uv is equal to the integral of udv plus v du. And we will try to transpose and solve for the integral of udv. The integral of udv, we will be placing this on the left side of the equation, thereby giving integral of udv is equal to uv minus the integral of v du. We call this the formula for the integration by parts, or we just simply call it IBP formula. So when and how shall we use the integration by parts formula? This formula is applicable to the product of two functions, and these two functions cannot be readily integrated using those formulas listed previously. The first step is to choose which among the terms of the product will be the proper u and the proper dv. And take note, the priority of choice for dv must be integrable by itself, and the u, on the other hand, must be differentiable. Let us illustrate that with this example. Let's say we wish to evaluate the integral of ln x dx. It seems like at first sight that this is not the product of two functions, but actually it is. If we let u be equivalent to ln x and dv will be equivalent to dx, if we take the differential of ln x, that will be dx over x. If we integrate dv is equal to dx, the term on the left is simply v, and the term on the right will become x. So v is equal to x. And recalling the formula for integration by parts we have derived, the integral of u dv is equal to uv minus the integral of v du. Looking at the assumptions that we made, the integral of u dv is actually the integral of ln x dx. U is ln x and dv is dx. This will be equivalent to uv. Our u is ln x, and then our v is x. So we could simplify that to be x ln x minus the integral of v du. Our v is x and our du is dx over x. So simplifying further, we could now say that the integral of ln x dx is equal to x ln x minus x plus the arbitrary constant c. Let us say we wish to evaluate the integral of x ln x dx. Here, this is a product of two functions. This is x and ln x. Since we do not have a ready integration formula for this function, we will integrate this by parts. Take note that the u must be differentiable and the dv must be integrable by itself. So if we will let u be equivalent to ln x, and then dv will be the other remaining parts of the integral, which will be x dx, we will take the differential of u, it becomes dx over x. If we integrate dv is equal to x dx, integrating the left side is just simply applying the property of integral that will be equivalent to v. And on the right side, we apply the general power formula. So v is equivalent to x squared over 2. And if we recall the IBP formula, that is the integral of u dv is equal to uv minus the integral of v du, all the terms in this formula are already available in our assumptions. So, uv is equivalent to ln x times x squared over 2, while our VDU, the integral of the VDU, is actually x squared over 2 times the integral of dx over x. If we simplify the first term, that becomes x squared over 2 times the ln of x. Take note, there's no need to simplify that or to integrate that because it is already an algebraic function. And for the second term, we brought out the constant, which is negative 1/2. That is now placed before the integral sign. So what remains is simply the integral of x dx, which is integrable by the general power formula. And integrating further, we take here x squared over 2 times the ln of x minus 1/2 x squared over 2 plus c. And if we simplify further, it will give us the final answer, the quantity x squared over 2 times the ln of x minus x squared all over 4 plus the arbitrary constant c. Let us evaluate the integral of x cubed e raised to x squared times dx. Here, we will be making our u be equivalent to x squared. We have to make it x squared so that the x remaining term is actually satisfying the differential of the exponent of e, which is x squared, which will become 2x dx. That is why dv will become x is e raised to x squared times dx. If we take the differential of u, that is 2x dx, and then if we integrate, dv is equal to x e raised to x squared dx, we get v is equal to 1/2 e raised to x squared. And now we will be applying the IBP formula. The integral of u dv is equal to uv minus the integral of v du. Our uv is actually x squared times the quantity 1/2 e raised to x squared minus the integral of v du. Our v du is 1/2 times the integral of e raised to x squared times 2x dx. The second term is already integrable. So our final answer is 1 half x squared e raised to x squared minus 1 half e raised to x squared plus c. Let us integrate the integral of x cosine 2x dx. We let u be equivalent to x and dx is cosine 2x dx. To take the differential of u, which is x, that will be simply dx. Integrating dv is equal to cosine 2x dx. We get v is equal to 1 half sine of 2x. Using the IBP formula, uv is actually 1 half x sine 2x. The integral of v du is actually 1 half sine 2x times dx. So, if we simplify it further, we get 1 half x sine 2x minus 1 half times 1 half of the integral of sine 2x times 2 dx. Here, we introduce 2 into the integrand and introduce the correcting factor of 1 half, thereby getting our final answer, which becomes 1 half x sine 2x plus 1/4 cosine of 2x plus c. So, ladies and gentlemen, I hope these examples will help you in the topic of integration by parts. You just solve again the other requirements that will be given in this unit. See you in the next presentation.